You've probably asked this question yourself. Maybe you were a child lying in the dark trying to fall asleep, staring at the ceiling. Maybe you read something or heard something, and it stuck in you the way a certain kind of question sticks. The kind that doesn't resolve cleanly, that keeps surfacing when the rest of your mind goes quiet. The question is this: the universe is expanding. Scientists say this with confidence. The galaxies are moving apart. The space between them is growing. This has been known since the 1920s, when Edwin Hubble mapped the distances to other galaxies and found that almost all of them were receding from us, and that the farther away a galaxy was, the faster it was moving away. The universe is getting bigger. And so the question forms, the way it always forms. Bigger means it was smaller before. Something that is growing must be growing into something. A balloon expands into the room around it. A bubble in water expands into the water. An explosion expands into the air. What is the universe expanding into? Here is the honest answer, the one that physics actually gives. Nothing. Not nothing in the sense that there is empty space out there waiting. Not nothing in the sense of a void that the universe is spreading across. Nothing in the strictest possible sense. There is no outside. There is no container. There is no room the universe is expanding into, no surrounding medium, no background space in which the universe exists. The universe is not expanding through anything. The universe is not expanding into anything. The universe is expanding, and that expansion is the only thing that exists. This is the answer that every physicist will give you. And it is an answer that your brain will initially receive and immediately translate into something easier, something that lets it find firm footing and move on. Your brain will hear expanding into nothing and construct a picture of a large bubble in the dark, growing, the darkness around it being the nothing. That picture is wrong. The darkness is not there. There is no edge. There is no outside. There is no around it. Those concepts do not apply. If you felt a slight resistance to that, a slight sense that the answer doesn't fully land, that resistance is correct. It means you understood the answer properly, because this is genuinely, deeply, not intuitive. It is not the kind of thing that becomes easy with familiarity. It becomes familiar, but it doesn't become easy. The physicists who work with this every day do not find it comfortable. They find it workable. Let me tell you something about that resistance, because it matters. The fact that your brain keeps reaching for an outside, keeps trying to imagine a room the universe is growing in, is not a failure of intelligence or imagination. It's an accurate reflection of every piece of experience you have ever had. Every object you have ever encountered exists inside space. Every process of growth or expansion you have ever seen has happened inside something larger. Your nervous system was shaped by 4 billion years of evolution on a planet where nothing in the environment suggested that space itself could be what's growing, rather than things growing within space. The difficulty of picturing this correctly is the difficulty of asking your brain to model something for which it has zero evolutionary preparation and zero perceptual experience. You are being asked to visualize a truth that no human has ever directly observed, that no animal has ever needed to navigate, that has no parallel in anything your senses have ever processed. The reason it feels strange is precisely because you're getting it right. Tonight, we're going to try to actually understand it. Not just accept it as a fact and move on. Actually understand it. The geometry, the physics, the specific way in which the universe is structured such that expansion doesn't require an outside, what the evidence says about whether the universe is finite or infinite, what dark energy is doing to the size of what we can ever see, and what it means, really means, that there are galaxies out there right now receding from us at speeds faster than light, that we will never see, that cannot send us a signal, that exist beyond a horizon we can never cross. Before we get started, if you love exploring the depths of space and the great unanswered questions of the cosmos as much as we do here, take a moment to like this video or subscribe to the channel. It helps more curious minds find their way here and keeps this journey going. Now, let's actually try to understand this. The first thing to understand, and this is the thing that everything else depends on, is what is actually expanding. When scientists say the universe is expanding, they do not mean that matter is flying outward through some pre-existing space, the way shrapnel flies outward from an explosion through air. That image, the explosion image, is wrong. It is the natural human image, an explosion, a beginning, things flying apart. And it is precisely the wrong picture. What is expanding is space itself. The galaxies are not, for the most part, moving through space. The space between them is growing. The fabric of space-time is stretching, and the galaxies are being carried apart by that, stretching the way dots on the surface of a balloon are carried apart when the balloon is inflated. The dots are not moving across the balloon's surface. The surface itself is growing. This distinction is not subtle. It changes the nature of the question entirely. If you fire a bullet through a room, the bullet is moving through the room, through pre-existing space. There is space in front of it. There is space behind it. The bullet travels from one part of space to another. Space itself is the container, the medium, the thing the bullet moves through. But if space itself is what's growing, then there is no container. There is no medium. There is no pre-existing region of space that the universe is moving through. The universe doesn't need an outside to expand into, because expansion in this sense doesn't involve moving through anything. It involves the stretching of the thing that already exists. Imagine you took a rubber band and stretched it. The rubber band doesn't move through the air around it. The air is irrelevant to the stretching. The rubber band itself is what stretches. Now imagine a universe in which the rubber band is all there is. No air, no container, no room. Just the rubber band and everything on it. When you stretch that rubber band, it gets longer. The things on it get farther apart. But there is no outside, because the rubber band is the entirety of what exists. This is much closer to what the expanding universe actually means. Space itself is what's growing. And the question, what is it expanding into, is like asking what's outside the rubber band when the rubber band is all that exists. The question contains an assumption that there must be an outside. That doesn't apply, but your brain keeps wanting to ask, okay, but what's outside the rubber band? Even imagining all there is as a rubber band, you can still imagine peering over the edge of the rubber band and seeing the air around it. So the rubber band analogy fails too. The failure is in the analogy, not in the physics. Every physical object you can imagine exists inside space. Every analogy you can build uses physical objects. So every analogy puts the universe inside something by default, because that's what all the things in your experience do. They exist inside space. The universe doesn't exist inside space. The universe is space, plus everything in it. There is no container that space sits in. Space is not a substance occupying a larger void. Space is the context in which everything exists, and it has no outside. Hold that. It won't become comfortable, but it will become workable. Because now we can start to understand what the expansion actually is, and what the question of expanding into what actually becomes when you take it seriously. Let's spend a moment on the balloon analogy. Because it's everywhere, because it's what most people have heard, and because getting it right, specifically getting the ways it fails right, will pay off significantly. in what comes next. The balloon analogy goes like this. Imagine the universe as the surface of a balloon. Galaxies are dots on the surface of the balloon. As you inflate the balloon, all the dots move apart from each other. Every dot sees every other dot receding. No dot is at the center. No dot is at the edge. Everything looks the same from every dot's perspective. And that's exactly what we observe. We see all distant galaxies receding from us, and the farther away they are, the faster they're moving. If another galaxy is twice as far from us, it's receding twice as fast. This scaling is called Hubble's law, and the balloon analogy explains it perfectly. There are two important things the balloon analogy gets right. First, there is no center of expansion. On the balloon's surface, there is no dot that is the origin, the point where the expansion started, and all other dots are moving away from. Every dot sees the same thing. The expansion is happening everywhere simultaneously, in the fabric of space itself. The Big Bang did not happen at a point in space. It happened everywhere in space, simultaneously. All of space began expanding at the same moment, and all of space has been expanding since. Second, the balloon's surface is a finite space, with no boundary and no edge. A two-dimensional being living on the surface of the balloon can travel forever in any direction and never reach an edge. The surface is finite. It has a measurable total area, but it has no border, no wall, no "you've reached the end" sign. It curves back on itself. A two-dimensional being traveling far enough in any direction will eventually return to where it started. Both of these features are real features of the actual universe. The expansion has no center, and the universe may have no edge. But the balloon analogy fails in a critical way that most explanations don't acknowledge honestly. When you inflate a balloon, the balloon's surface expands into three-dimensional space. The balloon exists inside a room. The room is the container. The balloon gets bigger, but the room was already there. So when you hear the balloon analogy, your brain does exactly what it's supposed to do. It pictures the balloon and the room, and it asks, what's the room? What is the three-dimensional space that the universe, like the balloon's surface, is expanding into? And the answer, done honestly, is the balloon analogy doesn't have an equivalent for that. The analogy is a 2D surface expanding in 3D space, used to represent a 3D space that doesn't expand into a fourth spatial dimension. The expansion of the universe is not the expansion of a 3D surface into a 4D volume. It is just the expansion of 3D space, full stop, with no higher dimensional container. The analogy gives you the right picture of what the surface does. It gives you the wrong picture of what the surface does it inside. There is no fourth spatial dimension for our universe to expand into. At least, none that we have any evidence for, and none that any current physical theory requires. The universe is not embedded in something larger. It is not a membrane floating in a higher dimensional void. It is not a bubble in a bigger space. These are things that appear in certain speculative theories, but they are not what general relativity, our best theory of space-time, requires or implies. What general relativity tells us is that space can be curved without being curved into anything. Curvature, in the mathematical sense that general relativity uses it, is intrinsic. It is a property of the space itself, not a description of how the space sits inside a larger space. A circle has intrinsic curvature. It doesn't need to be embedded in a plane for its curvature to exist. Similarly, our universe can have its geometry, including an expanding geometry, without being embedded in anything. This is genuinely hard to picture. It is hard to picture for very good reason. Every curved thing you have ever seen is curved inside a larger space. There are no everyday examples of intrinsic curvature, without embedding. The concept exists in the mathematics, and it is what the universe actually does. But it has no good everyday analogy because your everyday experience contains no examples of it. So when you ask, what is the universe expanding into? The honest answer is nothing, because the expansion is a property of space itself, and there is no external container. And the question assumes an external container that doesn't exist. But this still leaves several genuinely interesting and unanswered questions. About what the universe is, about what's beyond the part of it we can see, about whether it's finite or infinite, and about what dark energy is doing to the horizon of what we will ever be able to see. Let's go there. Here is a distinction that almost everyone misses, and that changes the entire picture of the question. When scientists show you a map of the universe, the beautiful spherical map of everything we can see, with the cosmic microwave background radiation as its outer shell, they are not showing you the universe. They are showing you the observable universe. These are two very different things. The observable universe is the part of the universe from which light has had time to reach us since the Big Bang, 13.8 billion years ago. Light travels at 300,000 kilometers per second, the fastest speed anything can travel. In 13.8 billion years, light can travel 13.8 billion light years. So you might expect the observable universe to be a sphere about 13.8 billion light years in radius. It isn't. It's larger, much larger. The observable universe has a radius of approximately 46 billion light years. Wait, how can light that has been traveling for 13.8 billion years have traveled 46 billion light years? That's more than 3 times further than light should have been able to go. This is where expansion enters in a way that confuses almost everyone. When a galaxy emitted the light we're now receiving, that galaxy was closer to us than 46 billion light years. But while the light was traveling toward us, the universe was expanding. The space between us and the galaxy was growing while the light crossed it. By the time the light arrived, the galaxy had been carried much farther away than it was when the light left. That galaxy is now, right now, as you listen, approximately 46 billion light years away. But the light currently reaching us from it is light that left when it was much closer. So the observable universe, the sphere of space from which we can currently receive light, has a radius of about 46 billion light years. Everything inside that sphere has had time to send us light, and that light has reached us. Everything outside it has not sent us light yet, or the light it sent hasn't reached us yet, or, because of accelerating expansion, never will. The total universe, the full extent of space and everything in it, is almost certainly larger than the observable universe, possibly much larger, possibly infinitely larger. We cannot know how big the total universe is, because we can only observe the part of it that's inside our observational horizon. Everything beyond that horizon is inaccessible to us not because of any barrier or wall, but simply because of the speed of light and the age of the universe. We haven't had time to see further, and because of what dark energy is doing to the expansion, we never will. Think about what this means. The universe we study, the one we map, the one we photograph with the James Webb Space Telescope, the one we describe when we talk about 2 trillion galaxies, is not the whole universe. It's a bubble, our bubble. The bubble defined by how far light has been able to travel since the Big Bang, inflated to its current size by the expansion of space. And that bubble sits inside something larger, much larger, possibly infinitely larger. The universe isn't expanding into something, but within the universe, our observable portion is a tiny, finite region of something that extends far beyond what we can see. There is a boundary in the universe, Not a physical wall, not a place where space ends, not an edge with a sign on it, but a boundary nonetheless. A boundary imposed by physics, by the speed of light, by the expansion of space and its acceleration, beyond which nothing can reach us and we can reach nothing. This boundary is called the cosmic event horizon. It sits at a distance of approximately 16 billion light-years from us. Everything inside that distance, every galaxy, every star, every photon currently en route, has the potential to eventually reach us. The light from those objects might take billions of years to arrive, but given enough time, it will. Everything beyond that horizon, every galaxy, every star, every civilization that might exist out there right now, cannot send us a signal. Not because they haven't tried, not because the signal hasn't left yet, but because the space between us and them is expanding faster than the signal can travel. The light they emit, moving toward us at 300,000 kilometers per second, is being outrun by the expansion of the space it's crossing. It will never arrive. Right now, there are galaxies beyond our cosmic horizon that we can still see. How? Because the light we're currently receiving from them left those galaxies billions of years ago, when they were within our horizon. But those galaxies have since receded beyond it. The light that left them a billion years ago is still on its way to us. But any light they emit today, any signal they send right now, will never reach us. They are still there, out there in the dark. But they are beyond reach, and this horizon is not static. It's not a fixed boundary that the universe grows past at some point in the distant future. It is a boundary that is constantly sweeping inward as the universe's expansion accelerates. More and more galaxies are crossing it. More and more of the universe is being placed beyond permanent reach. In the far future, in 1 trillion years or so, if our current understanding of dark energy is correct, the only galaxies visible from our local group will be the ones gravitationally bound to us. Everything else will have receded beyond the horizon forever. The night sky in that distant future will be dark, not because the stars are gone, because the stars have been carried beyond the edge of what is reachable. Whatever astronomers or whatever successors to astronomers exist in that distant future will look out at the sky and see a universe that looks much smaller than ours. They will see only the local group. If they had no records from earlier epochs, they might conclude that the local group is all there is. They would have no observational evidence of the vast cosmos we can see today. We are fortunate. We exist in what cosmologists sometimes call the golden age of cosmology, an era when the expansion has proceeded far enough for us to understand it, but not so far that the evidence of it has been erased. We can see the distant galaxies racing away. We can measure the cosmic microwave background radiation, the afterglow of the Big Bang, still visible from the edge of our observational horizon. We can piece together the history and structure of the universe from evidence that is accessible to us now, but will not be accessible to whoever or whatever exists trillions of years from now. Every year, a little more of the universe permanently disappears beyond the horizon. Every year, the observable evidence of the full extent of the cosmos diminishes slightly. We are racing against a one-way door. Let's address something directly that trips almost everyone up. Earlier I said that galaxies beyond our cosmic horizon are receding from us faster than light. And you might have thought, wait, nothing can travel faster than light. That's special relativity. That's one of the most fundamental laws of physics. How can galaxies be moving faster than light? The answer is that special relativity's speed limit applies to things moving through space. It does not apply to the expansion of space itself. This is not a loophole. It is not a technicality. It is a genuine physical distinction. When special relativity says nothing can travel faster than light, it means no object, no signal, No information can move through space at a speed greater than about 300,000 kilometers per second. The limit is on motion through the fabric of spacetime. The expansion of the universe is not motion through spacetime. It is the stretching of spacetime itself. When two galaxies are being carried apart by the expansion of space, neither one of them is moving through space particularly fast. The space between them is growing, and the growth of space has no speed limit. Here is the analogy that helps. Imagine you have a rubber band with ants on it. The ants can crawl at a maximum speed of, say, 1 centimeter per second. Now you stretch the rubber band. Two ants that are far apart may find themselves moving apart at 10 centimeters per second. Not because either ant is crawling faster than 1 centimeter per second, but because the rubber band itself is stretching. The constraint on ant speed doesn't apply to the stretching of the rubber band. Galaxies are the ants. The speed of light is the maximum crawling speed. The expansion of space is the stretching. Distant galaxies can be receding from us at many times the speed of light. And this doesn't violate special relativity because the galaxies aren't moving through space faster than light. Space between them is growing faster than light can cross it. This has one direct and deeply strange consequence. There are galaxies we can currently see in the sky right now, in the images from Hubble and Webb, that are receding from us faster than light. We can see them because the light they emitted long ago, when they were closer and the expansion was slower, has been traveling toward us all this time and has finally reached us. But any new light they emit right now is traveling away from us at the speed of light, while being carried away at an even higher speed by the expansion of space. That new light will never reach us. We are looking at these galaxies across billions of light years, receiving their ancient light. And at the same moment, those very galaxies are moving beyond our permanent horizon. The image we see is the past. The reality is already gone. This is a property of the universe that has no analogy in ordinary human experience. There is nowhere on Earth where you can see something that is simultaneously present in your view and permanently beyond reach. But in the universe, this is the situation for billions of galaxies. We see them. We cannot ever reach them. Any message we send will never arrive. And the situation is getting worse, because dark energy is accelerating the expansion. The rate at which galaxies are crossing the horizon is increasing. The observable universe, properly defined, the sphere of things that can never reach us, is shrinking. Here is where the question of what is the universe expanding into connects to a question that can at least partially be answered with observation. What is the shape of the universe? When cosmologists ask about the shape of the universe, they're asking about its geometry, specifically whether it is positively curved, negatively curved, or flat, in the technical sense that general relativity provides. A positively curved universe is like the surface of a sphere. Travel far enough in any direction, and you come back to where you started. The universe is finite, unbounded, and closed. If you looked far enough in one direction, assuming the universe were transparent and old enough, you'd see the back of your own head. In this universe, space has a total finite volume, like the surface area of a sphere has a finite total area. A negatively curved universe is like a saddle. Space curves away in every direction, and the universe extends forever, infinite, open, and never looping back on itself. Think of an infinitely large Pringle chip, curving away from any point you stand on. A flat universe, the third option, has the geometry you learned in Euclidean geometry. Parallel lines never meet. The angles of a triangle add up to exactly 180 degrees. Space extends without curvature in all directions, forever. All three options have no edge, in the sense of a wall or boundary. In the positively curved case, the universe loops back on itself. In the negatively curved and flat cases, it extends infinitely. None of them have an outside. None of them are embedded in a larger space that you could somehow stand outside of and look at. What do observations say? The most precise measurements of the universe's geometry come from detailed mapping of the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. Tiny temperature variations in this radiation encode information about the geometry of the universe. The spacing of those variations is sensitive to the curvature. In a positively curved universe, they would be slightly larger. In a negatively curved universe, slightly smaller. In a flat universe, a specific characteristic size. The measurements from the Planck satellite and from multiple independent experiments are consistent with a flat universe to within the measurement precision. Not perfectly flat. There is some small allowable uncertainty, but flat enough that any curvature is below our ability to detect. A flat universe is, on one level, a relief. It means the geometry of space is exactly what your intuition would expect. Euclidean, familiar, without the strange self-looping of a positively curved geometry. You could draw a triangle in space, and its angles would add up to 180 degrees. You could fire two parallel laser beams in the same direction, and they would never converge or diverge. But a flat universe is also, on another level, the most terrifying of the three options. Because a flat universe is infinite. Let's be careful here, because infinite universe is a phrase that gets used casually, in a way that doesn't communicate what it actually implies. An infinite universe means that space extends forever in all directions. Not very far. Not further than we can see. Forever, actual infinity. The same kind of infinity that mathematics uses. No endpoint, no boundary, no limit. In an infinite universe, the observable bubble we live in, the 46 billion light-year radius sphere of everything we can see, is an infinitesimally small fraction of the total. Not a small fraction. An infinitesimally small fraction. Whatever finite volume you assign to the observable universe, it is smaller than 1 divided by infinity. It is, compared to the total, effectively nothing. And in an infinite universe, everything that can happen does happen. Somewhere. This is the consequence that nobody talks about in polite company, because it sounds like science fiction, but follows directly from the mathematics of infinity. The observable universe contains a finite amount of matter arranged in a finite number of possible configurations. Two regions of the universe that are large enough and contain enough matter will, by the mathematics of combinatorics, have identical configurations simply because the number of possible arrangements of matter, while astronomically large, is finite. And infinity is larger than any finite number. At a distance of approximately 10 to the power of 10 to the power of 28 meters. A number so absurdly large that writing it out in digits would require more atoms than exist in the observable universe. There should exist, in an infinite universe, a region of space that is an exact copy of our observable universe. Not a similar region. An exact copy. With a copy of Earth. With a copy of you lying wherever you're lying right now, listening to a copy of this video, having this same thought. This is not mysticism. It is the logical consequence of the mathematics. An infinite universe with the same physical laws and a finite number of matter configurations must repeat. The repetition is not optional. It follows from the definition of infinity. Whether this is terrifying or profound depends on your perspective. Some people find it comforting. In some sense, you exist infinitely many times in an infinite universe, and you will never truly end. Some find it disturbing. The uniqueness of your life, your choices, your specific consciousness, is undermined by the existence of infinite copies. Some find it simply baffling, which is perhaps the most honest response. But this consequence, the repetition, the infinite copies, is what an infinite flat universe actually implies. It isn't science fiction. It is the direct mathematical implication of the observations we have made. And the observations say the universe is flat, or very close to it. Let's talk about the thing that is actively, right now, tonight, making the question of what the universe is expanding into more urgent and more strange. In 1998, two independent teams of astronomers studying distant supernovae made a discovery that earned the 2011 Nobel Prize in Physics and overturned a central assumption about the universe. They found that the expansion of the universe is not slowing down. It is speeding up. After the Big Bang, the expectation was that the universe would expand, but that gravity, the mutual attraction of all matter for all other matter, would gradually slow the expansion down. Maybe enough to eventually stop it and reverse it into a big crunch. Maybe not that much, but at least enough to cause the expansion to decelerate over time. The supernova observations showed the opposite. Distant supernovae were dimmer than they should have been if the expansion were decelerating, meaning they were farther away than expected, meaning the expansion had been faster in the recent past than it should have been under the decelerating model. The expansion was accelerating. Something was pushing the universe apart, overcoming gravity, driving galaxies away from each other faster and faster. That something was given the name dark energy. It represents approximately 68% of the total energy content of the universe, making it the dominant component by far. Ordinary matter, stars, planets, gas, dust, everything we can see and touch, is only about 5% of the universe's energy content. Dark matter, which we infer from its gravitational effects but cannot directly observe, is about 27%. Dark energy is the remaining 68%, and it is the dominant force shaping the universe's fate. What is dark energy? Honestly, we don't know. The simplest explanation, which fits the data well, is that it is a property of space itself. Empty space has an intrinsic energy density. It is not nothing. Even vacuum, the absence of matter and radiation, contains energy. This is consistent with quantum mechanics, which predicts that empty space seethes with virtual particle activity and has a non-zero ground state energy. The cosmological constant, which Einstein introduced into his equations of general relativity and later famously called his greatest blunder, turns out to be real. Space has energy, and that energy is driving the accelerating expansion. The consequence of accelerating expansion for the question we started with is this. The cosmic horizon, the boundary beyond which signals can never reach us, is not moving outward as the universe ages. It is moving inward. Dark energy is accelerating the recession of distant galaxies, pushing more and more of the universe's volume beyond the point where its light can ever reach us. Every galaxy that crosses the event horizon is lost to us forever. Not inaccessible. Lost. There is no technology, no future advancement, no imaginable method that could retrieve information from beyond the horizon once the expansion has carried it past. The information is gone. The light that left that galaxy before it crossed the horizon is still en route and will eventually arrive. But after that last light arrives, the galaxy is dark, unreachable. For all practical purposes, it ceases to exist for us, even though it continues to exist for itself. Right now, in real time, as you listen to this, galaxies are crossing that boundary. Not one, millions of them, continuously. Every day, more of the universe becomes permanently inaccessible. And the rate is increasing. Dark energy is not constant in intensity. It appears to be constant in density, meaning that as the universe grows and creates new space, the total amount of dark energy grows with it. More space means more dark energy, which drives more expansion, which creates more space, which creates more dark energy. This feedback is why the expansion is accelerating rather than maintaining a constant rate. The universe, in a real sense, is eating itself, creating more of itself in order to create the energy that drives the creation of more of itself, and in doing so, progressively locking away more and more of its own contents behind a one-way door. Here is something that scientists have known about for decades, and that deserves far more public attention than it gets. Our galaxy, the Milky Way, and the entire local group of galaxies around it, Andromeda, the dwarf galaxies, everything in our gravitational neighborhood, are moving. Not just being carried by the expansion of the universe, actually moving, in addition to the expansion. Moving through space at hundreds of kilometers per second toward a specific direction in the sky. Not only are we moving that direction, every galaxy in the local universe, for a radius of hundreds of millions of light years, is moving in the same direction. The Virgo cluster, the Centaurus cluster, galaxies spanning an enormous volume of space, all flowing, all converging on a single point in the sky, in the direction of the constellation Centaurus. Something is pulling them. The source of this pull, whatever massive concentration of matter is generating the gravitational force that is accelerating hundreds of millions of light years of galaxies in a single direction, is called the Great Attractor. It sits at a distance of about 250 million light years from us, in a direction that happens to lie near the plane of the Milky Way, where our own galaxy's gas and dust block our view of the universe behind it. For decades, we couldn't see the Great Attractor directly because we were looking through the Milky Way's obscuring plane. X-ray and radio observations, which penetrate the dust more effectively than optical light, have revealed what appears to be the source. An enormous supercluster of galaxies called the Norma Cluster, at the heart of a larger structure called the Hydra Centaurus supercluster. But even accounting for the Norma Cluster and the surrounding superclusters, the gravitational pull is larger than what we can see. The observed mass doesn't fully explain the observed motion. Further investigation led to the identification of an even larger structure, the Shapley supercluster, approximately 650 million light-years away, the most massive structure in the observable universe. A concentration of galaxies so dense and so massive that it extends the gravitational influence felt by the Milky Way across hundreds of millions of light-years. When you add the Shapley supercluster to the calculation, the numbers get much closer to matching the observed motions. But not perfectly. There remain anomalies. There remain flows of galaxies that suggest something else, perhaps something beyond our observational horizon, also contributing to the pull. Perhaps a structure so large that part of it is within our observable universe, and part of it is beyond the cosmic horizon, contributing gravitational influence through a region of space from which no light will ever reach us. This is one of the most haunting possibilities in modern cosmology. That the universe we can see is not all the universe there is, not just in theory, not just because the math implies it, but because we can measure it. The motion of galaxies, including our own, hints at something beyond what we can observe, something that is affecting us gravitationally even though it cannot send us light. We are being pulled towards something we cannot see, something that may be beyond the horizon, in the part of the universe that is permanently inaccessible. And we know it is there because we can feel its weight. The universe is not just expanding into nothing. It is also, in its local structure, falling towards something in the dark. If you traveled outward from Earth in any direction, past the planets, past the stars of the Milky Way, past the Andromeda Galaxy, past the Virgo cluster, past the Shapley supercluster, past everything we can see with any telescope we have ever built, you would eventually reach a point where the universe stops being transparent. Not because there's a wall, not because space ends, but because the universe used to be opaque. For the first 380,000 years after the Big Bang, the universe was so hot and so dense that it was filled with plasma, a state of matter in which electrons are stripped from atomic nuclei and move freely. In a plasma, photons, particles of light, cannot travel far before being scattered by the free electrons. The early universe was a fog, opaque. Light couldn't get through. If you had been inside the early universe and tried to look in any direction, you would have seen nothing but a glowing, luminous fog in every direction. An orange-white hot plasma filling all of space. As the universe expanded and cooled, about 380,000 years after the Big Bang, something changed. The temperature dropped to approximately 3,000 degrees Kelvin. Hot, but not hot enough to keep the electrons stripped from their nuclei. They recombined. Atoms formed. Hydrogen atoms, helium atoms. And the moment those atoms formed, the universe became transparent. For the first time, photons could travel freely. The fog lifted. All the light that had been trapped in the plasma, scattered endlessly, was suddenly released. It streamed outward in every direction across the newly transparent universe. That light is still traveling. We can still see it. In every direction we look, if we tune our instruments to the right wavelength, we detect this light, the afterglow of the moment the universe became transparent. In 13.8 billion years of expansion, the light has been stretched by the expansion of space from visible light to microwave wavelengths. It is now called the cosmic microwave background, the CMB. It fills all of space at a temperature of approximately 2.725 degrees above absolute zero, uniform to about 1 part in 100,000 in every direction. This is the oldest thing we can see. Nothing older. Because before 380,000 years after the Big Bang, the universe was opaque. No light escaped. No light traveled. Nothing is observable from that era. Whatever happened before 380,000 years is hidden behind the CMB. The surface of last scattering, the name physicists give to the moment when the fog lifted and the CMB photons began their journey, is the absolute edge of our visual universe. At a distance of approximately 46 billion light-years in every direction, the CMB forms a sphere around us. Not a physical sphere, a temporal one. The light arriving from that distance right now left its source 13.8 billion years ago, when the universe was 380,000 years old. We are seeing in every direction simultaneously the universe as it existed at that first moment of transparency. What the CMB looks like, in detail, is extraordinary. It is not perfectly uniform. It has tiny fluctuations, temperature variations of about 1 part in 100,000, tiny hot and cold spots scattered across the sky. These fluctuations are the imprints of quantum fluctuations in the very early universe. Density variations so small they were quantum in origin, stretched and amplified by the rapid expansion of the early universe into the seeds of all cosmic structure. Every galaxy, every cluster, every supercluster, every void in the universe we can see today grew from those tiny CMB fluctuations. The patterns in the CMB are the blueprint that produced everything. The Planck satellite mapped the CMB in unprecedented detail. What it found confirmed the standard cosmological model with remarkable precision. The pattern of fluctuations matched predictions. The universe is flat, consistent with infinite extent. Dark energy is real. The relative proportions of ordinary matter, dark matter, and dark energy are what the equations required. Everything checked out, except for a few things that didn't. There's another thing the James Webb Space Telescope found when it started looking near the edge of the observable universe that disturbed astronomers far more than the Hubble tension. The galaxies at the edge of what we can see are different from what the standard model predicted. Not different in the subtle ways that require careful statistical analysis to detect, different in ways that were immediately obvious to anyone looking at the images. They're too big, too bright, too mature, too early. The standard model of galaxy formation is built on a well-understood framework. The universe starts with tiny density fluctuations. Dark matter begins collapsing into halos under its own gravity. Ordinary matter follows. Gas cools and fragments into stars. The first stars form about 100 to 200 million years after the Big Bang, and galaxies assemble gradually over hundreds of millions of years, growing by merging with smaller galaxies and accreting gas from their surroundings. Large, mature, well-organized galaxies take a long time to form. You wouldn't expect to find a galaxy with the mass of the Milky Way in place and running smoothly only a few 100 million years after the Big Bang. There simply hasn't been enough time for that much matter to find each other, collapse, and organize. The first deep field images from JWST showed massive, bright, apparently well-formed galaxies at redshifts that correspond to just 300 to 500 million years after the Big Bang. Not hints of galaxies forming. Galaxies, large ones, with hundreds of billions of stars already in place. Joe Leger, an astronomer at Penn State, who was part of one of the first teams to analyze these objects, described it as like showing up to an archaeological dig and finding a full Roman Colosseum, where you expected to find a few scattered huts. The scale of the discrepancy between prediction and observation was large enough that it wasn't a matter of fine-tuning the model. Something fundamental might be wrong. The initial wave of alarm has been tempered somewhat by continued analysis. Some of the early candidates turned out to be somewhat lower redshift than first measured, closer in time to us, and therefore less anomalous. Some of the brightness estimates were refined downward. The systematic uncertainties in interpreting these observations are real and significant. But even accounting for all the measurement uncertainties, there appear to be more massive early galaxies than the standard model predicts. Not one or two anomalies. A population of them. A statistical excess that is hard to explain away. The explanations that have been proposed are fascinating and varied. Some invoke a higher rate of star formation efficiency in the early universe. Early gas clouds converting more of their mass into stars than later gas clouds do. Some propose that certain early galaxies go through brief periods of extreme brightness, appearing more massive than they are, and that JWST is catching many of them in these brief flares. Some suggest that the initial perturbations from inflation, the period of rapid expansion in the very earliest moments after the Big Bang, were not the smooth, single-scale fluctuations the simplest models predict, but had more power at certain scales, allowing more structures to collapse earlier. And some suggest that the problem points to something more fundamental about the standard model, that the history of structure formation in the universe is genuinely different from what we thought. JWST has been looking at the universe for only a few years. The data is extraordinary in quality, but limited in quantity. The field is still actively arguing about what it means. What is certain is that the standard model of how the universe makes galaxies has been challenged. And the challenge came from the most powerful telescope humanity has ever built, looking as close to the edge of the observable universe as any instrument has ever managed. The edge of what we can see is not confirming everything we thought. It is raising questions. Here is something that follows directly from what physicists believe about the Big Bang, almost inescapably, and that most science communication handles carefully or avoids altogether. If the Big Bang happened, and if it was driven by a process called inflation, the extremely rapid expansion of space in the first fraction of a second, that all current models require to explain why the CMB is so uniform, why the universe is so flat, and why we see the specific pattern of fluctuations we observe, then an enormous number of additional universes almost certainly also exist. Not as a separate speculation, as a consequence of the physics. Here is the logic. Inflation is the theory that in the first approximately 10 to the minus 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26, doubling every tiny fraction of a second, expanding so rapidly that regions of space that were in contact with each other were flung to opposite ends of the observable universe before light could travel between them. This explains why the CMB looks the same in opposite directions of the sky, even though those regions were so far apart that they couldn't have come to thermal equilibrium by ordinary processes. Inflation is driven by a quantum field, the inflaton field, that has enormous energy density in a false vacuum state. The field is like a ball sitting on a hilltop. It's in a high energy configuration and will eventually roll down to a lower energy state, releasing its energy and ending inflation. That release of energy is, in a sense, what the Big Bang is, the inflaton field rolling to its minimum, converting its potential energy into the hot plasma that became the early universe. Here's where the multiverse enters. In quantum mechanics, transitions between states happen randomly, driven by quantum fluctuations. For the inflaton field to end inflation, it has to quantum tunnel from its high energy state to its low energy state. And this tunneling doesn't happen uniformly everywhere at once. It happens randomly, in patches, at different times, in different regions of space. In any given region, there's a probability per unit time that inflation ends. But while inflation is proceeding at its frantic pace, the universe is expanding far faster than the patches where inflation has ended can grow. New regions of inflating space are being created faster than inflation is ending in any particular region. This is called eternal inflation. Once it starts, it never stops globally. In the overwhelming majority of space, inflation continues forever. In small bubbles that nucleate randomly throughout the inflating background, inflation ends. The inflaton field rolls to its minimum. Energy is released. Matter and radiation form. And a hot Big Bang begins inside that bubble. That bubble expands, cools, forms galaxies and stars and planets. From inside that bubble, it looks like the entire universe, which is exactly what it is, from the perspective of anything inside it. But from outside, from the perspective of the inflating background, it is a tiny bubble in an infinite sea of ongoing inflation, surrounded by other bubbles, each one a separate universe that also began with its own Big Bang, each one potentially with different values of the physical constants, different particle masses, different strengths of fundamental forces, different amounts of dark energy. Our universe is one of those bubbles. This is not a metaphor. This is what the physics implies if eternal inflation is correct. And while eternal inflation is not proven, it may not be provable, given that we cannot see outside our own bubble. It follows from the same physics that explains the CMB fluctuations, the flatness of the universe, and the uniformity of the early universe. The theory of inflation that explains what we observe also implies eternal inflation as a logical consequence. Let's be precise about what may not be provable means here, because it's important. Science progresses by making predictions that can be tested. A theory that makes no testable predictions is not science. It's philosophy or metaphysics, depending on how you feel about it. The classic criticism of the multiverse is that it is empirically empty. It predicts the existence of other universes that are by definition beyond our observational horizon, and therefore no observation could ever confirm or deny it. This criticism is partly right, but not entirely right. Eternal inflation does make some predictions about our observable universe. The specific pattern of CMB fluctuations, not the fact of inflation which is testable, but the detailed statistics of the fluctuations, can in principle discriminate between different inflationary models, some of which predict eternal inflation more strongly than others. The search for primordial gravitational waves, which would be produced by inflation and could be detected in the polarization of the CMB, is one active area of testing. A detection of primordial B-mode polarization in the CMB at the right amplitude and scale would be strong evidence for a specific class of inflationary models, and would simultaneously be evidence for the conditions that produce eternal inflation. The bubble collision signature, the ring-shaped imprint on the CMB that would result from our bubble universe colliding with another bubble, is also in principle detectable. No unambiguous detection has been found, but the absence of a detected collision constrains rather than rules out the multiverse. It tells us that bubble collisions within our past light cone are rare, which is consistent with the most common inflationary scenarios. So the multiverse is not entirely beyond testing. It is not, however, directly confirmable in the way that the existence of, say, a new elementary particle is confirmable. The best we can say is that the physics that we have confirmed implies eternal inflation, and eternal inflation implies the multiverse. The multiverse of eternal inflation is, as we said, infinite. Infinitely many bubble universes, each one separated from all others by an infinite inflating void. The physical constants can differ between bubbles because the inflaton field's final resting state, the value it settles to after inflation ends and the Big Bang begins, can vary. In some bubbles, the electron mass is different. The fine structure constant takes a different value. The ratio of dark energy to matter is different. The number of dimensions of space is different. In some bubbles, atoms cannot form. In some, chemistry cannot happen. In some, the universe expands so fast that nothing has time to collapse into galaxies. In the subset of bubbles where the constants happen to fall in the range that permits complexity, observers can exist. We are in one of those bubbles. This connects directly to one of the deepest puzzles in all of physics, the fine-tuning problem. The physical constants of our universe appear to be extraordinarily, suspiciously well-suited to the existence of complex structures and life. The ratio of the electromagnetic force to gravity is approximately 10 to the 36. If it were even slightly different, if electromagnetism were a bit weaker or gravity a bit stronger, stars would burn out in thousands of years rather than billions, and the complex chemistry of life would have no time to develop. The mass of the Higgs boson, which gives elementary particles their mass, is about 17 orders of magnitude lighter than the natural scale suggested by the Standard Model. If it were its natural mass, atoms wouldn't exist. The cosmological constant is 120 orders of magnitude smaller than theoretical predictions, as we've discussed. Every one of these constants appears to be finely tuned for life to exist. There are two ways to respond to this. The first, the constants are finely tuned because they were set by something, a creator, a designer, a deeper principle we haven't found, that intended a universe compatible with life. This is a metaphysical position that physics can neither confirm nor refute. The second, the constants appear finely tuned because we exist in the subset of an infinite multiverse, where they take life-permitting values. In the infinite ensemble, no value is improbable. Every value exists somewhere. We observe the values we observe because we are observers, and observers can only exist where the constants allow for observers. Neither answer is satisfying in the deepest sense. The first invokes something outside physics. The second explains the fine-tuning by making the fine-tuner unnecessary, but at the cost of requiring the multiverse, which is itself a commitment of extraordinary philosophical weight. The universe is not just expanding into nothing. It may be one of infinitely many universes, each one expanding into nothing, each one separated from all others by an inflating void that has no end and no edge. Each one, a bubble of local physics in a background that is not physics as we know it. The multiverse doesn't make the original question go away. It multiplies it. What is the inflationary background expanding into? What is outside all the bubbles? The answer is still nothing, but a different kind of nothing. The nothing at the edge of a structure that is itself infinite and expanding. We are nested inside nothing, inside nothing, inside nothing. Every layer of the answer is another version of the same answer. Now let's talk about the dark flow, which is one of the most controversial and unsettling observational claims in modern cosmology. In 2008, a team of researchers led by Alexander Kashlinsky at NASA's Goddard Space Flight Center published a paper claiming to have found evidence that the entire observable universe, every galaxy we can see, in every direction, is being pulled in a specific direction by a gravitational source so massive and so distant that it lies beyond our cosmic horizon. Not just our galaxy, not just our local group, not just the local supercluster, all of it. Every galaxy cluster in the observable universe, to the limits of their measurement, exhibiting a coherent bulk flow, a motion that cannot be explained by the gravitational influence of anything we can see. The method used was the kinematic Sunyaev-Zeldovich effect, a small but measurable change in the temperature of CMB photons as they pass through galaxy clusters. When CMB photons interact with the hot electrons in a galaxy cluster, they gain a small amount of energy. If the cluster is moving relative to the CMB, this energy shift is slightly asymmetric. Photons scattered by electrons moving toward us gain slightly more energy than photons scattered by electrons moving away from us. By measuring this effect across thousands of galaxy clusters, you can, in principle, detect the bulk flow of those clusters. Kashlinsky and his team measured this effect and found what they claimed was a coherent flow. Galaxy clusters across the observable universe, all exhibiting a correlated motion toward a specific direction in the sky, far exceeding what should be caused by the local gravitational influences we can observe. If real, the dark flow implies the existence of a massive concentration of matter, far beyond our observable horizon, in a region of the universe from which no light can ever reach us, whose gravitational influence extends across tens of billions of light-years to affect the motion of everything we can see. Something so enormous it dwarfs the Shapley supercluster and every other structure in our observable universe. Something we can feel but cannot see because it sits beyond the one-way door. The dark flow has been one of the most actively debated claims in cosmology since it was first published. The original analysis was re-examined by other teams using the Planck satellite's CMB data. The Planck team, in a 2013 paper, found no statistically significant bulk flow of galaxy clusters in the direction claimed by Kashlinsky. Their analysis suggested that the claimed signal was within the expected range of statistical fluctuations. Kashlinsky's group responded with refinements to their analysis. The debate has continued in the literature. As of the current state of the field, the dark flow remains contested, not definitively confirmed by independent analysis, but not definitively refuted either. It sits in the uncomfortable zone of observational claims, where the signal is below the threshold of certainty, but above the threshold of dismissal. If it is real, the implications are extraordinary. A source of gravity beyond our horizon, detectable only through its influence on everything we can see, would mean that the structure of the universe extends far beyond the observable bubble in ways that are not predicted by simple models of inflation. It would mean that the cosmic microwave background, the oldest light we can see, contains imprints of structure that formed beyond the current horizon, structure that was once in causal contact with our region during the inflationary epoch and has since been separated by the expansion. It would mean that the universe beyond our horizon is not a featureless, uniform extension of the universe we can see. It has structure. It has concentrations of matter so enormous they dwarf anything in our observable volume. And we cannot see them, cannot visit them, cannot send them a signal. We can only feel their gravitational reach across billions of light years of expanding space, as a tiny, coherent tug on everything we can observe. Whether the dark flow is real remains to be established by future observations, deeper surveys of galaxy cluster velocities using the KSSZ effect, more precise CMB polarization maps, better characterization of the peculiar motion field across larger volumes. What is real, what is not contested at all, is that the structure of the universe beyond our horizon is, in principle, unknowable by direct observation. We are inside a bubble of observability, and whatever exists outside that bubble is beyond us in the most literal possible sense. The dark flow, if confirmed, would be the nearest thing to a window into that beyond that physics can offer. Not a view, but a shadow. Not the light, but the gravity. The universe pulling on itself from beyond its own edge. Let's talk about where all this expansion leads. Not just where it leads in theory, but what the universe will actually look like, if anything is left to look, in the deep future. Because the question of what the universe is expanding into connects directly to the question of what that expansion is producing over time. Right now, we are in a particular moment in the universe's history, a brief window, cosmologically speaking, in which the universe is neither too young nor too old. Young enough that stars are still burning, galaxies are still forming, the CMB is detectable, the evidence of the Big Bang is still legible in the structure of the cosmos. Old enough that complex chemistry has had time to produce planets, biology, and consciousness. This window will not last. In roughly 5 billion years, the Sun will exhaust its hydrogen fuel and expand into a red giant, ending the possibility of life on Earth. The Milky Way and Andromeda will begin their collision and eventual merger, producing a new combined galaxy that astronomers have nicknamed Milkomeda. The universe will be roughly 18 billion years old, already ancient by human standards, but young by the timescales we're about to discuss. Over the next 100 billion years, the rate of star formation across the universe will decline. Gas reservoirs are being depleted. The fuel for new star formation is being consumed. Stars are dying faster than they are being born. In roughly 100 trillion years, 100,000 billion years, the last red dwarf will exhaust its hydrogen. The universe will produce no more stars. Everything from that point on is the era of remnants. White dwarfs, the cores of dead stars like the Sun, will cool slowly over hundreds of billions of years toward absolute zero. Neutron stars, the crushed remnants of heavier stars, will spin down and cool. Black holes, which have been absorbing whatever passes within their reach, will be the dominant remaining structures. In this era, the night sky, if any mind exists to observe it, which seems implausible, would be dark. Not the darkness punctuated by stars that we know. Actual darkness, The only light sources would be the faint glow of cooling white dwarfs, slowly fading toward invisibility over timescales that dwarf the entire current age of the universe. But dark is not empty. The structures of matter, the remnants of galaxies, the white dwarfs and neutron stars and black holes would still exist. The expansion would continue, carrying those remnants apart from each other as dark energy drives the universe toward ever lower density. Then, over timescales of 10 to the 34th years or longer, proton decay, predicted by many grand unified theories of particle physics, though not yet observed, would dissolve ordinary matter. Every proton in every white dwarf and every cold rocky body in the universe would eventually decay into lighter particles, disintegrating the last solid matter into radiation and leptons. The remnants of stars and planets, cooling in the dark for trillions of years, would quietly dissolve into nothing. Black holes would remain. Hawking radiation, the slow evaporation of black holes through quantum effects near their event horizons, would gradually drain their mass over incomprehensible timescales. A stellar mass black hole would take roughly 10 to the 67th years to evaporate. A supermassive black hole, like the one at the center of the Milky Way, would take on the order of 10 to the 100th years. 10 to the 100th years. A googol years. The current age of the universe is approximately 10 to the 10th years. The last black hole will evaporate in a time that is 10 to the 90th times the current age of the universe. A number so large that it has no analogy in any human experience or any physical scale you have ever encountered. After the last black hole evaporates, the universe will contain only the products of evaporation: photons, electrons, positrons, neutrinos, spread across a volume that has been expanding for a googol years. Those particles will be separated from each other by distances so vast that they will essentially never interact. The universe will be in a state of maximum entropy. No energy gradients, no usable energy, no process that can do work. The universe will be cold, dark, empty, and forever. This is the heat death, the maximum entropy final state, the terminal condition toward which dark energy is driving the universe. And here is the final strange truth about the expansion. The heat death doesn't mean the universe stops. The universe keeps expanding. There is no state of zero volume. There is no collapse. The universe grows and grows and grows forever, becoming less dense, colder, more uniform. The remnants of everything that ever existed separated by ever-increasing voids, until every particle is isolated from every other particle by distances that light can never cross. Not because light doesn't exist, not because space ends, because the space between every particle is expanding faster than light can cross it. Every particle will eventually be beyond the horizon of every other particle, each one alone in its own observable universe, a universe of one. This is what expanding into nothing eventually produces: an infinite universe in which every piece of it is alone, in which every particle's horizon contains only itself, in which the universe has expanded into a structure so rarefied that it is, in all functional senses, the nothing it was expanding into. The expansion creates what it was expanding into, gradually, over unimaginable time. That is either profound or terrifying, depending on where you're standing. Let's go to the deepest version of the question. Not, what is beyond the observable universe? That has an answer, even if we can't observe it directly. More, universe. But what is outside the universe itself? What is beyond space and time? What surrounds the totality of existence? Stephen Hawking had a way of answering this that is among the most precise and most unsatisfying answers in the history of physics. He used the analogy of the North Pole. If you're standing at the North Pole and someone asks you, "What's north of here?" the question doesn't have an answer, not because you don't know. Because north is a direction defined on the surface of a sphere, and at the North Pole, every direction is south. There is no north. The question isn't just unanswerable, it's malformed. It contains an assumption that north exists as a direction from every point. That isn't true at the North Pole. Asking what came before the Big Bang, or what exists outside the universe, is, Hawking argued, a similarly malformed question. Time began at the Big Bang. Before the Big Bang, there was no time, and therefore no before. Outside the universe, there is no space, and therefore no outside. These words, before, outside, require the existence of time and space to mean anything. Asking what's outside space is like asking what's north of the North Pole. The question assumes something that doesn't exist in the situation you're describing. This is either a complete answer or no answer at all, depending on your philosophical commitments. The physicists who find it satisfying argue that it is the best possible answer, that the question is dissolved rather than answered, because the dissolution is more honest than a false answer would be. There is no outside, not because it's empty, but because outside is a concept that requires space to have meaning, and space is what the universe is made of. The philosophers who are not satisfied argue that dissolving the question is not the same as answering it. They point out that Hawking's argument applies within the framework of general relativity and standard cosmology, and that asking what's outside the universe is precisely a question about whether that framework is complete, about whether space and time are truly fundamental, or whether they emerge from something more basic that might exist before and beyond them. This is a live question in theoretical physics. There are research programs, most notably loop quantum gravity and various approaches to quantum gravity, that treat space and time not as fundamental features of reality, but as emergent properties of a deeper quantum structure. In some of these frameworks, there is something before the Big Bang in a meaningful sense, not in time, because time didn't exist, but in whatever the deeper structure is that time emerges from. The Big Bang is not the beginning of everything in these frameworks. It is the beginning of the specific phase of the deeper structure that we recognize as our universe. If this is correct, then what's outside the universe might have an answer. Not an answer in spatial terms, not a place you could travel to, but an answer in terms of the deeper substrate from which space and time emerge. The universe would exist inside a more fundamental reality, the way a wave exists inside an ocean. The wave is real. The ocean is also real. The wave doesn't contain the ocean, but the ocean contains the wave. This is speculative. There is no experimental evidence for any specific quantum gravity theory. The project of quantum gravity, reconciling general relativity with quantum mechanics, is one of the great unsolved problems of physics, unresolved for decades. And no leading candidate theory has yet produced a testable prediction that has been confirmed. But the question of whether space and time are fundamental or emergent is real and active. And if they are emergent, if they arise from something deeper, then asking what's outside space and time becomes genuinely a meaningful question with a possible answer. An answer in terms of the deeper structure that gives rise to space and time. An answer that physics doesn't have yet. This is the honest frontier, not a blank wall, but a genuine open question that the best minds in theoretical physics are working on, without a clear path to resolution. There is one more thing worth discussing before we close, because it connects the question of what the universe is expanding into to the question of what the universe fundamentally is. Dark energy, the energy that is driving the accelerating expansion, is, in the simplest model, the energy of empty space. The quantum vacuum has an intrinsic energy density. Space has energy just by existing. This energy is what the cosmological constant represents. The problem is that the value of this energy density, as measured by cosmologists from the expansion of the universe, is approximately 120 orders of magnitude, 10 to the power of 120 times, smaller than what quantum field theory predicts it should be. This is not a small discrepancy. This is the largest discrepancy between a theoretical prediction and an observation in the history of physics. It is not a case of getting the second decimal wrong. It is a case of getting the answer wrong by a factor that, written out in full, would be a 1 followed by 120 zeros. Let's put that in context. The number of atoms in the observable universe is approximately 10 to the 80th. The number of possible chess games is roughly 10 to the 120th. The discrepancy between the quantum field theory prediction for vacuum energy and the observed value of dark energy is larger than both of these numbers. It is, by some measures, the largest single numerical discrepancy in the history of human scientific measurement. If the vacuum energy density were anywhere close to what quantum field theory naively predicts, the universe would have expanded so rapidly in its first moments that no structure could ever have formed. Not just no life, no atoms, not just no planets, no galaxies. The energy density would have driven the expansion so fast and so furiously that even the first atomic nuclei would never have had time to find each other, much less form atoms, much less cool into gas clouds, much less collapse under gravity into stars. The universe would have expanded instantly into an essentially featureless, infinite void of free quarks and leptons, never complexifying, never organizing. We are here. Therefore, the vacuum energy is not what quantum field theory predicts. It is 10 to the 120 times smaller, and nobody knows why. Every proposed solution to the cosmological constant problem either requires some extraordinary coincidence that seems physically implausible, or some new symmetry or cancellation mechanism that has never been observed and makes no other testable prediction, or simply defers the question by replacing the original problem with an equivalent one in different language. Supersymmetry, the theory that every known particle has a supersymmetric partner, was once hoped to explain the small value of the cosmological constant through cancellations between the vacuum energies of particles and their superpartners. No supersymmetric particles have been found, despite extensive searches at the Large Hadron Collider, and the simplest supersymmetric models would have predicted particles at masses that have now been ruled out. Supersymmetry may still be real at higher energies, but the simple version that would have helped with the cosmological constant appears not to be the version nature chose. String theory contains an enormous landscape of possible vacuum states. Estimates of 10 to the 500 possible configurations of the extra dimensions that string theory requires, each one corresponding to different values of the physical constants, including the cosmological constant. The anthropic argument in the string theory context says that most of these vacua have cosmological constants too large for life, and that we live in one of the rare vacua where the cosmological constant takes a small enough value that structure can form. This is a version of the same multiverse argument we discussed for eternal inflation, and carries the same philosophical weight and the same difficulty of direct testing. Dynamical dark energy, the possibility that the cosmological constant is not actually constant but varies slowly over time, would, if confirmed, rule out the simplest vacuum energy interpretation and require a new physical field driving the expansion. Several current and near-future experiments, including the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope, are measuring the history of the expansion in detail to look for evidence of variation in dark energy over time. As of writing, the data is consistent with a constant dark energy density. But the precision required to detect small variations is just now being reached. The cosmological constant problem is not a peripheral puzzle. It sits at the intersection of our two best theories of physics, general relativity and quantum mechanics, and reveals that they are incompatible at a deep level. The universe, as described by general relativity, has a cosmological constant that is tiny. The universe, as described by quantum mechanics, has a vacuum energy that is enormous. Both descriptions are confirmed in their own domains to extraordinary precision. But put them together, and they predict completely different things about the same number. This incompatibility is the heart of the quantum gravity problem. Until we have a theory that combines general relativity and quantum mechanics, a theory of quantum gravity which does not yet exist in fully tested form, we cannot resolve the cosmological constant problem. We cannot explain why the engine of the universe's expansion has the value it has. We cannot explain at the deepest level why the universe is expanding at the rate it is. The universe is expanding into nothing. It is expanding at an accelerating rate. The acceleration is driven by a property of space itself, whose value we cannot derive from first principles. The expansion will eventually isolate every particle from every other particle in an infinite, cold, dark void. And the deepest reason for all of it, why space has this energy, why the energy has this value, why the expansion is this fast, is currently beyond our ability to explain. This is the honest frontier of the answer. Let's come back to the question one more time. Not to answer it again, we've established that the physical answer is nothing and unpacked what that means. But to look at the question itself from a different angle. When someone lying in the dark asks, "What is the universe expanding into?" they are asking something real, not just a physics question, something existential. The question is a symptom of a discomfort, the discomfort of encountering a system that has no outside, no context, no frame of reference beyond itself. The discomfort of the bubble. We experience everything from inside something. We experience rooms from inside rooms. We experience galaxies from inside the Milky Way's disk. We experience the observable universe from inside its 46 billion light-year sphere. We always have a context, a larger frame, a beyond. When we discover there's more universe beyond what we thought was the edge, we feel relief. There's more. There's still a context. The bubble still sits inside something. The question is driven by that relief-seeking impulse. But the question, what is the universe expanding into, is the question of what happens when you run out of beyonds, when the largest frame there is has nothing outside it, when there is no further context to appeal to, when the question of what's around it has the answer, nothing, and that nothing is not a place. The brain resists this. It keeps constructing an outside. It keeps placing the universe inside a room, even knowing intellectually that the room doesn't exist. This is not a cognitive failure. It is the perfectly appropriate response of a mind that has been built by billions of years of evolution inside spaces that always have outsides, inside contexts that always have larger contexts. Your nervous system was shaped to navigate an environment in which everything you encounter is embedded in something larger. It was not shaped for the case where the largest thing is not embedded in anything. There's something in that resistance worth looking at directly. The resistance isn't random, it's pointing at something. The question assumes that the universe needs an outside, that there must be something for it to expand into, that a structure without a context is incomplete, that there's something missing about a universe that doesn't have a surrounding. This assumption is built into every human language, every physical intuition, every way of relating to space that has ever developed in the history of our species. And the question is asking, is there something the universe is incomplete without? Is there something that the universe is missing? Is there something it needs that it doesn't have? The physics says, no. The universe doesn't need an outside to be complete. It doesn't need a container to be real. It doesn't need a context to be what it is. The universe is. That is sufficient. That is all it is required to be. But notice what happens when you hold that answer. There's still a residue, still a reaching, still a sense that the universe, having no outside, leaves something unaccounted for. Something the physics doesn't reach. What the question is actually asking underneath all the physics is, am I inside something that makes sense? Is the universe I'm inside oriented? Does it have a context that gives it meaning? Is there a frame outside all frames from which the whole thing can be seen and understood? The question isn't really about physics. It's about whether existence itself has a structure that contains meaning. Whether the universe is the kind of thing that can be understood from the outside, in a larger context, or whether it is simply what it is, self-contained, self-referential, without justification or frame. The physics answer is, it is simply what it is. The expansion is real. The nothing beyond is real. The universe doesn't reach into anything beyond itself, because there is no beyond. Whether that is the complete answer depends on what you think questions are for. If questions are requests for information within the framework of physical science, expanding into nothing, and the expansion requires no outside, is complete. If questions are reaching for something wider, for the kind of understanding that situates existence inside a larger meaning, then the physics answer is not the full answer. It is the full answer of one kind. It is not the full answer of the other. This is where physics ends and something else begins. Not religion necessarily, not mysticism, but the simple, honest recognition that there are questions that physics answers completely within its domain and does not address outside its domain. The question of what the universe is expanding into is, physically, answered. The question of whether the universe exists inside a larger meaning is not a physics question. It is a question that your mind generates, legitimately, and that no measurement will resolve. The two questions are running together when someone asks, what is it expanding into? Physics separates them. The first question has an answer. The second doesn't have a physics answer. What it has is a human answer, or many human answers, none of them physical. And that is fine. That is how the boundary between physics and everything else actually works.